with respect to the exam, what I did was I looked at, and I'll show you this at the beginning of next class, I looked at what sort of percentage of the homework that people had gotten done before the exam versus their exam grade. And so pretty much if you had basically completed the homework before the exam, you were pretty much guaranteed to pass based on how the scores went. Okay? Those who, and then, because it's like mastery-based stuff, it's if you get it done eventually, you get a fairly high score. And I didn't look into it too much, but it looks like the people who were kind of in the 60 to 80 range on the exam may have had some trouble with the homework, but did it, right? So they did what they were supposed to do, but maybe we could have had more conversations or asked more questions. So what I'm going to ask folks to do, okay, so if you are a person who was kind of in the 60 to 80 range, so you passed, but you may not have done as well as you'd like, what I'd like you to do is you can go into like the study center. Let me go, I don't know if I can quickly log into Cengage. Let's see. If it has my, and I want you to, so after you look at the answer key, which I'll post after class, I want you to go into the kind of study center and, make yourself like a practice quiz for the, for chapters 4 and 5, okay, and then, and do it, and then get back, try to figure out what the things were that you didn't quite understand, and then, contact me for help explaining them and things like that. And I think that will get you sort of where you need to be, okay? And so just a quick how to find that, if I can, there we go. Here it is. So the little person at the desk icon, that's the study center, and you can create a new quiz using, chapters 4 and 5, all right, a number of questions, and then say, take the quiz, and it does it. So you can give yourself a little extra practice and then try to figure out, sort of what it was between that and comparing your exam to the answer key. And then we can work on just those things that gave you trouble, okay? So something that was a general, that's weird. Let's do this. Tablet's thinking too many things at one time. Okay. All right, so one of the things that is just, it's common for it to be kind of something it takes students a while to get, is when to use the prefixes and when not to, okay? So remember that we only use prefixes when we have covalent compounds. And so how do we know if we have a covalent compound? It's if we're dealing with just nonmetals, okay? You have an ionic compound if you're dealing with something from the left side and something from the right side, okay? So if you have a metal and a nonmetal, those are going to be ionic. Ionic compounds, we just give the name of the ions, and remember, no matter what, unless it's a polyatomic ion, whether it's an ionic compound or a covalent compound, the end of our name is going to end with IDE, okay? All right, so, all right, but, in general, there were a number of people who had their second exam grade was significantly better than their first, so good job changing your habits or whatever or on your improvement. And as a whole, the class did well, considering the fact that this was material that you were, learning in an almost, in an online environment, because I was gone for a couple of lectures and you had to watch the videos. So we didn't have time for much of a back and forth. So anyway, so on the whole, good job. And we'll work on the things that need to be fixed. And I'll try to reinforce things. So as we're working with compounds, as we go through the rest of chapter 6 and 7, I'll just keep using the names for things. And the more names you see, and the more we point out, hey, this is ionic, hey, this is covalent, then we'll get to where we need to be. All right. So where we need to be today is doing more Lewis structures, okay? So remember, we have this kind of procedure where we're going to be determining how many electrons we have, and then figuring out who's the center atom, putting single bonds between the center atom and everybody else, then adding electrons to the outer atoms, okay, to fill their valences, okay, and then looking at the center atom, getting it to an octet, or in the case again of some of our elements that can have expanded valences, which remember beyond the third row, and so phosphorus and beyond is those who can have that expanded valence, okay? All right, so when does our expanded valence happen most? Phosphorus and beyond. So beyond the third row. All right, so here's where phosphorus is. It is in the third row. So when we get to higher atomic numbers than that, that's when we can get those expanded valences. So let's talk about another exception, which is when we'll talk about what we call electron deficient atoms, okay? This is going to be the case where we have a central atom, okay, that don't have a filled valence shell, okay? Doesn't have a filled valence shell. So this is another one of our exceptions, okay? So generally, these are atoms from group 2 or group 3A. So this would be atoms from group 2A and 3A, okay? And then and when the outer atoms are hydrogen or other atoms that don't form multiple bonds. So atoms are hydrogen or those that can't form multiple bonds. And remember, the multiple bond formers are carbon, nitrogen, oxygen, phosphorus, and sulfur, okay? So not carbon, oxygen, nitrogen, phosphorus, or sulfur, okay? So that's kind of the condition, okay? So let's look at one of these. So we've got BF3 is the compound that we want to look at. Okay, so we have something that's in group 3A, boron, and we have fluorine that's in group 7, and it will only form one bond, right? All right, so let's count our atoms. So we've got boron, we've got fluorine, going to count our electron. So how many valence electrons does boron have? It's in group 3A. So it's going to have 3. And we've got one of those atoms. Okay. All right, fluorine is in group 7. So we have 7 valence electrons. And we have 3 of those. So that's 21 electrons. Okay. So we have a total of 24 electrons that we're going to place. Okay. Is this an ionic or a covalent compound? BF3? Let's name it. So let's look at our periodic table. Okay. So boron is not a metal, it's a metalloid, okay? And fluorine is definitely a nonmetal. So, and also boron, if we go and look at our common ions, right? Boron doesn't form an ion, aluminum does, but boron won't, okay? So this is going to be a covalent compound. And we call it binary because it only contains 2 elements, okay? So we would call so we'd name this, and we could use the prefix mono before the boron. Typically, if there's only one of them, we just use the name. So we could say monoboron, or we could say boron, okay? And then we have 3 of the fluorine. Since it's covalent, we're going to use tri. So we would call it boron trifluoride, okay? So that's how we'd name it, right? Okay, so our central atom. So we've got 24 electrons. So now we're going to arrange our atoms. We're going to put the boron in the center because it's farther from fluorine than fluorine is, right? And then we'll put the fluorines on the outside. Okay. Okay. All right. So we're going to add our single bonds. So I'll put those in pink. I'm going to add our electrons in pink. Okay. So we've got 3 bonds, okay? So that's 6 electrons that we've placed, okay? So we've got, 18 more electrons? All right, so let's add them to our outer atoms. So I'm going to start by giving each fluorine 2. So that's 6. And then, when we add the other ones in, okay? So when we give each one 6 electrons, each fluorine gets to 8 electrons around it, right? So this is because we've got 6 lone pair electrons and 2 bonding electrons. So so each of the fluorines has the octet rule satisfied. Okay. All right. Now, when we look at the boron, okay, the boron itself has only 6 electrons around it. Okay. So one of the things that we could do if we were drawing a Lewis structure is what? We could, take one of our lone pairs and make this a double bond, right? And then we'd satisfy the octet rule for everyone. And that's normally what we would do, okay? But it turns out, okay, this is one of those exceptions to our Lewis structure rules because when we actually look at this material, boron trifluoride, okay, the bond lengths are such that it tells us that these are all single bonds, okay? So it also, the reactivity of the compound is consistent with this being the correct Lewis structure, okay? So again, this atom here, okay, boron, is, again, one of those exceptions. And because this is, all right, so one thing, experimental evidence. Tells us that we don't really form double bonds with one of the fluorines. Oops. And so what is that experimental evidence? The first thing is the bond lengths, okay? We're going to be talking about bond lengths and how a single bond is longer than a double bond and a double bond is longer than a triple bond. So basically, the more connections you have between atoms, the tighter and closer they are together, okay? So when we look at the structure of this material, okay, what we see is something more reflective of single bonds, okay? So bonds are closer to single bond length. And then the second thing has to do with reactivity. Okay? So if this boron actually made a double bond with one of the fluorines, okay, it would satisfy the octet rule, okay, and it would be a happy atom. Okay? And so we would expect the material to be not as reactive as if that boron were what we call electron deficient. It only has 6 electrons around it in those bonding electrons. And so if it, in fact, does just have, single bonds, okay, that leaves this atom, okay, in search of 2 electrons, which means the compound is going to be more reactive, okay? So, let's say reactivity is consistent with an electron-deficient boron, which means it's more reactive, okay? Because that boron, again, why do atoms, chemicals react with one another? They react in such a way to take care of their electron needs, as it were, okay? All right. So this material, okay, is very reactive. So this is very reactive material, right? And so it's gonna, if it finds another compound, chemical, that has a lone pair, it's going to react with it like very readily. Okay, so when you have boron trifluoride, okay, so I'm just going to draw it down here. So this is going to be an example of its reactivity. So we've got our fluorines, okay, and if we look at ammonia, not the ammonium ion, but ammonia, which is NH3. The Lewis structure for NH3 looks like that, and it's got a lone pair, okay? So this lone pair, okay, enables the ammonia to react with the boron trifluoride and form the following compound. We've got our fluorine, and then we've got the boron, and we've got our nitrogen with its hydrogens, and that bond forms between them right there, very readily and very easily. Okay. So hopefully you're getting a little glimpse of how knowing what the valence electron structure of an atom is and being able to draw a Lewis structure can tell us about something about what types of molecules our molecule might react with. Okay. All right. Now, again, this is, this happens under certain circumstances, right? If we have an element in group 2A or 3A, okay, and the atoms on the outside, the outer atoms are hydrogen, or those that can't form multiple bonds, okay? With this compound in particular, okay, we're, again, going to return to the theme of fluorine having a very high affinity for electrons, okay? So you can kind of think of why we don't form a double bond with one of the fluorines is that, they're willing to share to satisfy their need for an extra valence electron, but they're not willing to share those lone pair electrons because they have a very high affinity for electrons as an atom. Okay, so it's a little harder to identify which compounds are going to have an electron deficient central atom, but these guys are the rules that you're going to follow. Okay, and you're also going to be looking for fluorines. Okay. Okay, so again, what are our rules? When we have somebody in group 2A or 3A, that would be our central atom. And then we're going to eliminate those that can form double bonds, right? So C, N, O, P, or S. Those guys would not in the compound. Okay, so we would not have these as outer atoms. Okay, and then also hydrogen is going to be another thing that we look for. Okay. All right. So that's our electron deficient compounds. Okay. All right. I just spoiled it and actually gave you an example that used ammonia. So we've already drawn the ammonia Lewis structure, but let's just confirm that what I drew was right. Okay. So we've got nitrogen, we've got hydrogen. Right. Nitrogen has how many valence electrons? What group are we in? Yep. So we got 5 valence electrons. Hydrogen has 1. We've got 3 of those. So we've got, oops, just do this. Be consistent. All right, so we've got 13 electrons to place. Our central atom is never hydrogen. Okay, so we're going to arrange our atoms. We're going to make our bonds. So we'll make 1 bond to each. So we're over here. All right, and now we have to figure out, yeah.
Isn't the hydrogen only 3 total electrons?
Oh, yeah, I'm sorry. 1 times 3 is 8. Where the hell did I come up with that? Jeez. 3. You know what it was? I added 8. I went to total electrons in my head and then wrote it down and then did more math. Oh, thanks. All right. Yeah, that would have been a problem when we get to this next step, right? So after the bonds, we've placed 6 electrons, right? Because each one of these is 2 electrons. All right, so our remaining electrons, okay, are going to be lone pairs on the nitrogen. So we need to place 2 electrons on the central atom as a lone pair. And there we have it. Okay, so let's just check the octet rule. So nitrogen has 6 bonding electrons and 2 lone pair electrons, so that's 8 electrons. So that's satisfied the octet rule. And each hydrogen is participating in 1 bond, and we know that's what hydrogen does, right? It wants to get to 2. So that's our correct Lewis structure for, and this is a molecule called ammonia. That is a common name, okay? So ammonia is what we call the common name. All right, is this a covalent or an ionic compound? What is it? Yes, it's covalent, as you whisper, right? We're drawing Lewis structures of covalent compounds, so they're all going to be covalent, right? But we can name it, right, with our prefixes. So this is going to be either mononitrogen, tri-high, and remember we end with IDE, so trihydride, or nitrogen trihydride. It's going to be the name of that compound, okay? So this is a covalent compound, and there is also the ammonium ion, which is a polyatomic ion. So it is, if we brought a proton to this compound, okay, so let's make the ammonium ion, okay? So I'm going to start with this compound here. There we go. All right. And I'm going to add a proton to it, okay? So it's not coming with any electrons, okay? So this thing right here, okay, is starting out neutral. There we go. And I'm going to add, we call hydrogen ions protons because the most common isotope of hydrogen has no neutrons in the nucleus. So if you have H+, you have a proton in the nucleus and you've removed its electron, so all you have is a proton, okay? So this is a positive charge, right? So the compound we're going to make from this has a positive charge, okay? So what's going to happen is our proton, okay, is going to form a bond with the nitrogen right here, okay? So the nitrogen is going to donate both electrons to the bond, okay? This is when we study acids and bases, we'll talk about things called Lewis bases. And Lewis acids. This is the type of reaction you get when you have one atom contributing 2 electrons to a bond, okay? So the compound that we get, okay, has 4 hydrogens bonded to it, okay? But it has a net positive charge because this thing started out neutral and we just added another proton into the mix, okay? So we would put the positive charge there. So this is our polyatomic ammonium ion, okay, which is one of the ones that I asked you to memorize because it's very, very common. Yeah? Oh, you can. You can either do it kind of on the nitrogen, or you can do the bracket and the plus sign outside. Yeah. All right. So now we're going to draw some what we call organic Lewis structures. So organic molecules, okay, are carbon-based compounds. And so you're, again, with carbon-based compounds, with organic compounds, okay, they are going to feature mostly carbon and hydrogen and occasionally other molecules. So let's do this one right here where we've got 4 valence electrons on carbon because it's in group 4. And we have 2 carbons. Whoops. And we have hydrogens. We've got 6 of those. All right, did I count the electrons up right this time? Now we have 14 electrons. All right, now when you see something like this for an organic compound, okay, when we get to the arranging the atoms, okay, there isn't one central atom, right? So organic compounds are often written to show us kind of groups of atoms together, okay? So we can think of these as kind of 2 CH3s together, okay? So we know that the hydrogens are not going to be the central atoms, so what we're going to do is we're going to draw the carbons, okay, as the central atoms, okay? And we'll draw the hydrogens arranged around them, and we're going to give each carbon 3 hydrogens, okay? And then we're going to add our bonds. Okay, so we'll put 1 between the 2 central atoms and 1 to each hydrogen. All right, so what we're going to do first is let's just count our electrons. So we added our single bonds. So now we're going to ask, are there any extra electrons? Right, so here we go. So we've got 2 electrons here, 2 here, 2 here. So we've got how many bonds? 1, 2, 3, 4, 5, 6, 7 bonds. So we've got 7 bonds times 2 electrons per bond. It's going to give us 14 electrons. Okay, so in this case, we have placed all of our electrons, so we don't need to add any lone pairs, right? So, no lone pairs needed. But we need to figure out, do I need to somehow add double bonds? So we need to check and make sure that the octet rule is satisfied, okay? And so, if we look, each hydrogen is involved in 1 bond, okay? So all hydrogens in 1 bond. So check, that checks out. Okay. Now carbon is going to have, when it satisfies the octet rule, it will have 4 bonds around it. So each of these carbons has 4 bonds. So that makes 8 electrons around it. So it satisfies the octet rule. Okay. All right, so this is a molecule called ethane. Okay. And we're not going to get into naming organic compounds because that's a whole course in and of itself. Okay. All right. So let's look at this molecule now. Okay, so this is ethane. All right, and when we add what's called a hydroxyl group to it, okay, we get a molecule some of you may be familiar with, ethanol. Okay. All right, so here we go. We have a similar situation. We have 2 carbons, right? So we've got 4 valence electrons times 2 carbons, so that's 8. And then we have hydrogens. Each one has 1 valence electron. We only have 5 this time, so that's 5. Oops, nope, we have 6. I forgot this one, right? That's 6. So that's 6. All right, and then we have 1 oxygen. Oxygen is in group 6A. Okay. So that has 6 electrons. Oops. That's 6 valence electrons times 1 atom. This is valence electrons, number of atoms. Okay. So that's 6. All right, so we've got 8 plus 12, that's 20 electrons we're going to have to place. Okay. All right, so the central atom. So I got an oxygen here, okay? In this compound, okay, the carbons were the central atoms. Is oxygen going to knock carbon out of the running for central atom status? What's our rule for central atom? Farther from fluorine, right? So oxygen is closer to fluorine, right? So our carbons still stay at the center, okay? And the way this is written right here, the way the formula is written, gives us an idea of how to place the outer atoms, right? We're going to place 3 hydrogens around here. We'll place 2 hydrogens here. And then this is what we call a functional group, okay? Oops. In organic compounds, and it's called a hydroxyl, this particular one. Hydroxyl groups make alcohol compounds, compound class called alcohols. And so those atoms are going to wind up going together. Okay. All right, so now the next thing we do is we're just going to make a single bond between everybody, okay? 1. All right, so let's count up our electrons and see how we're doing. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 single bonds times 2 electrons per bond. So that's 16 electrons have been placed. So how many lone pairs do we need to place? We need to place 2 lone pairs, okay? So we need to place 4 electrons, which equals 2 lone pairs. And remember that we always start placing lone pairs on the outer atoms. So who is the only outer atom who can take lone pairs? Oxygen. So we're going to put 2 lone pairs on the oxygens. Okay. And now we're going to check our octet rule because we've placed all of our electrons. Okay. All right, all the hydrogens in one bond, they're good. All hydrogens in one bond, so check. Our carbons are each in 4 bonds, right? So carbons are in 4 bonds, so that checks out. Now let's check our oxygen. Oxygen has 2 bonds, that's 4 electrons. And then it's got 2 lone pairs, which is another 4 electrons. So it's got 2 bonds and 2 lone pairs. So that checks the octet rule as well. Okay? So this is the Lewis structure for ethanol. Okay? And one of the nice things about organic chemistry is, again, you're only using a few elements and you use them all the time. So, hopefully you draw enough Lewis structures, you'll realize that, oxygen is always going to be involved in 4 bonds, no lone pairs. Carbon always involved in 4 bonds, no lone pairs. Oxygen is usually going to be 2 bonds with 2 lone pairs. Okay? And you'll see that pattern over and over and over again. Hydrogen always involved in 1 bond. So let's look at this molecule now, okay? And I can't tell you the name of this until we do the Lewis structure because of organic chemistry naming rules. So let's give it a try, okay? All right, so we've got carbons and hydrogens in our compound. We've got 1, 2, 3 carbons. So 4 valence electrons times 3 atoms, that's 12 electrons. Okay. And then we have, I'm going to count them correctly this time, we've got 3, 4, 5, 6 hydrogens. So we've got 1 valence electron times 6 hydrogens, and that's 6. So we've got a total of 18 electrons, okay? All right, so again, with organic chemicals, they're kind of written in chunks so you know how to place your atoms. So we've got 3 carbons, and one will have 3 hydrogens around it, and one will have 1, and one will have 2. Okay? All right, so these are our, these are our little molecular chunks, as it were. Oh, I'm bad at the drawing today. There we go. Okay, so now let's add our single bonds. 2, 3. So we've added single bonds to everybody, okay? Can anybody see something that's immediately obvious to you? Yeah.
Carbon only has 3 single bonds.
Yeah, we have carbons that only have, 2 carbons that only have 3 single bonds. So let's just do this as if we were doing lone pairs, right? So we've got 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 bonds times 2 electrons per bond. So that's 16 electrons. So that means that we would normally place like 1 lone pair, right? So we need to place 2 electrons, okay? But if we place them on either one of these carbons, okay? So let's just say we place them here, okay? Now let's check our octet rule. Or actually, I'm going to be more, let's place it here because that's closer to being an outer atom, right? And all right. So now we check the octet rule. This carbon has 4 bonds around it, 8 electrons. This carbon has 3 bonds and 1 lone pair. That has 8 electrons, right? So this has 8 electrons around it. This has 8 electrons around it. This poor guy only has 6 electrons, right? So now we have to start thinking about multiple bonds, okay? And carbon is one of those atoms that can form multiple bonds. So what we're going to do is we're going to take this lone pair, okay, and we're going to make a double bond, okay? And then everyone will have the octet rule satisfied. So I've got my hydrogens, got 1 hydrogen here, and I've got 3 on this one. Okay, so that's the Lewis structure of this molecule. Okay, and this one has it. So this one has a slightly more complicated name. Okay, so I called this molecule ethane. Okay, we use the A when we have all single bonds. Okay, this one has 3 carbons, so it becomes something that has a PROP in the beginning of the name. When it has a double bond, we change the ane to ene. So this is propene, this molecule. Okay. All right. Okay, so what I want you to do is we didn't do did we do SF4 before? Let me check. I want to check what we did for expanded valence, and then let's see. We did not. Okay, so at home, try drawing SF4, okay? And we'll start with the answer on the slide on Wednesday. And then And then we're going to go into talking about polarity and molecular structure, okay? All right, have a good Monday, folks. This week in lab, you are going to be weighing your alum, and then I believe, I forget what the next lab is, but